section 5.4 worksheet. We have the answers here. And number 6, they've given us a integral of a derivative here. And if we want to integrate this argument, okay, ultimately we're going to find the derivative of this. Now keep in mind that when we have a derivative of something, when we find a derivative, is there more than one derivative when we find it? If I find the answer to this, whether it's an easy function or not, okay, is there any more answers, or is there one answer to this? Just this part here only. There's one answer. Okay, whereas if we integrate something, okay, there's more than one answer because we'd always have to put plus what on the end? Plus c. But there's not that issue when we differentiate. If we differentiate, everybody in the class should get the same answer for this no matter what. True? So ultimately, if we integrate the derivative of something, okay, ultimately we're asking for what's the antiderivative of the derivative of this function. So wouldn't the antiderivative here be simply the radical x squared minus 1? Wouldn't that be the antiderivative and evaluated on 1 to 4? True? And again, if we find the derivative and then we antidifferentiate, we'd get right back to what we started with. True? And remember, if we did antidifferentiate, we'd get plus c, but remember with the first fundamental part of the fundamental theorem, we can use any antiderivative. So we'll use the one where c is 0 as normal. So in evaluating, again, ultimately what happens with the derivative and the integral here in this problem? They ultimately just do what? They cancel each other out. We just need to evaluate it from 1 to 4, and that'll give us our answer. So if we evaluate here, we're going to get the square root of 15 minus square root of 0, which ultimately equals square root of 15. Anything else on 5.4 worksheet? Jeff? And number 3, we have, again, an f function that we have to find the derivative of. And so ultimately we have 2 variable limits. So remember what we want to do to remedy that is we want to write the first one from 0 to x of 1 over t dt. And then, whoops, the farthest one I should say, 2x we want to have in the first one. And then we subtract the one that's closer to the origin, if you will. Alright. And so with that, if we take each of those individual expressions, which ultimately are equal to these two individuals are equal to the original integral, and then we do the derivative separately, then we ultimately get 1 over 2x times 2 minus 1 over x. And again, remember in this one we have to do the integrand evaluated at the upper limit, so we're putting a 2x in there, and then multiplying by the derivative of the upper limit, which is 2. And so ultimately what happens with the 2's here? Those cancel, so we get 1 minus x minus 1 minus x, so ultimately the answer is what? 0. Others on the 5.4 worksheet. And number 5, again, we got the derivative here, and the issue here is that we do have just a variable upper limit, which means that the first fundamental theorem applies. So if we plug in our 1 minus x into the integrand evaluated at the upper limit, and then times the derivative of the upper limit, we know the derivative of that function, 1 over x, is negative 1 over x squared. If you don't have that memorized yet, you could use the quotient rule, or you could make it a power function and use the power rule. Okay? But ultimately that's our derivative. So with that said, we'd have 2x times negative 1 over x squared, which ultimately would give us negative 2 over x. So again, derivative of the upper limit is this, so 2x. 2 over 1 over x is just 2x, and we multiply those two, the x's will cancel the bottom one and top the other, and leave us with negative 2 over x. Anything else on the 5.4 worksheet? Alright, let's take a look at the 5.5 worksheet. The issue here says that the given is a trapezoidal approximation, and the question is in the first part here, look at our solutions. They gave us, we can see that the numbers that we're putting into the trapezoidal rule, which I'll go back to, put that below, is these numbers that we're putting in the parentheses here, we're cubing them. Okay? The 2's are part of the trapezoid rule. Okay? So ultimately, what's our function then? We're taking x values and we're cubing them. So what function is it that we're? That's the cubic function. So ultimately, that's why we're going from 0 to 2 of x cubed dx. And keeping in mind that you'll notice that how much we're going by 0.05 to get from x value to x value. True? So the key is, how many subintervals would that be? And again, the 0 to 2 part is here. We're going from 0 to 2. That's why at 0 to 2 we're putting in a 0 first and then the 2 second, so that's our first and last x values. And ultimately, we have a 1/40th out here because of the fact that, again, on the subintervals we're going by 0.05. So ultimately, if we did from 0 to 2, if we did 10 subintervals, we'd be going by 0.1s, wouldn't we? Okay. So if we do 20 subintervals, we'd be going by 0.05s. Okay. And so ultimately the subinterval length would be 1/20th. True? And that's why what's out in front? 1/40th, because of the fact that 1/20th over 2 is 1/40th. Okay? So again, we're just recognizing that this is just a trapezoidal approximation for that particular function. Alright, and then the other questions we're supposed to ask here is which is greater, the integral or the trapezoidal approximation? Keep in mind that this function, remember, that has to do with concavity. And since x cubed would be concave up on that interval, then the trapezoids would be above the curve. So the trapezoid approximation should be above. And ultimately that's what it says in the part here. It's concave up, so therefore the trapezoids are above the curve, so the trapezoidal approximation would be greater. Okay. The other ones on here, I'm just going to put the answers up here. We can take a look. We have the set that we have in there gives us the function here is x over 4 from 2 to 20. The trapezoidal approximation in here would be equal since the integrand here is a line. If it's linear, the trapezoids are just going to be on the line. Okay? Therefore, it's going to be exactly the same. So we end up with 99 halves. All right. And then in the third one, we'd recognize that one hopefully as Simpson's rule because of the 4s, if you will. The 4, then 2, then 4, then 2. And we're putting our numbers into radical x. And we're putting in a 0 and a 2. But again, it's not just 2 subintervals because we can see that there's more than 3 entries there. So it looks like we have going from with our 6 subintervals, looks like putting in a half. We put in a 0 here on the left end point. Put in a half on this one. A half, the square root of a half is 1 over radical 2, which is radical 2 over 2. Then we're putting in a 1. We're putting in a 1 and a half. Then a 2, 2 and a half, 3, 3 and a half. Actually, I lied. Half. Oh, we're going to 0 to 4. Sorry, because ultimately the result is what we see here. Remember, we're not seeing what they put in, but remember if we count the way we did it here. 0, half gives us that. 1 gives us that. 3 halves. 2 in here gives us that. 5 halves. 3, 7 halves, 4. And remember that matches up because 4 gives us a 2 when we put it into the radical. So ultimately we're going from 0 to 4 with subinterval length of 2, or excuse me, a half. And that's why we have 1/6 out here. It's a half over 3. And ultimately our Simpson's rule for approximation for that is 99 halves. Or nope, I lied, wrong problem. 16 thirds, I should say. And if we do the same thing with the trapezoidal rule, we'd ultimately set up the same way. We'd have a quarter out in front because it's h over 2 instead of h over 3, so on. And then ultimately the question is compare the Simpson's rule and the trapezoidal approximations geometrically, which do you think should be bigger? And the explanation there is the fact that that's concave down. the function in question is concave down, so therefore we'd have underestimate with the trapezoidal rule. Okay. And Simpson's rule, we're using the same intervals here, but they'd be curved segments. So ultimately the curved segments would be essentially above the straight segments, if you will. So Simpson's rule should be larger, and if you check those two out, we do in fact get Simpson's rule being larger than the trapezoidal rule. Questions on that one?
How do they, I just don't get how you choose the interval, like how do you move it from 0 to 4?
Well, ultimately, you're putting a 0 into the function and you get 0, right? And you're putting something into the function and getting 2. So think about what is that something that you would put into that function to get 2?
How do you know what the function is?
Well, ultimately, you just look at what the y values are. You're getting 0, then you're getting radical 2 over 2, then you're getting 1. Even if you just looked at the whole number of parts here, you're putting in 0, 1, and then if you put in 2, you get radical 2, then radical 3, then radical 4. And if you check your halves here, you got 1/2 square root would be that. If I put 3 halves in there, I get radical 6 over 2, and so on. And ultimately, just determine how are these, what kind of function would give me these y values was what it boils down to. Okay. And I guess to start with, looking at the fact that you got a 0, a 1, a radical 2, a radical 3, and a radical 4. So just look at the y values and see if you can determine, that's kind of the puzzle of the deal, is to try to figure out what are we doing to these x values to get these said y values. Okay. I mean, if they gave us that function, we could clearly, write out the sequence without any trouble whatsoever. Okay. But the question is, can you look at the sequence and then go back to the function? So that's kind of the skill that we're doing, just going backwards. So it takes a little practice, and just gonna think about what function might give you those particular numbers. All right. Anything else on the those worksheets?